For centuries, astronomers relied on a single tool to study the universe: their own eyes. They built larger lenses and better mirrors, but they were ultimately restricted to the narrow band of visible light. That left humanity completely blind to some of the cosmos's most dangerous forces. In September of 1859, an astronomer named Richard Carrington was sketching a group of unusual sunspots. Without realizing it, he had just witnessed an intense solar flare, the origin of a massive, invisible wave of charged plasma hurtling directly toward Earth. Less than 18 hours later, that coronal mass ejection slammed into our planet's magnetic field. While the storm itself was entirely invisible to human observation, its effects were immediately felt by the global telegraph network. Telegraph operators across Europe and North America reported sudden catastrophic system malfunctions. They experienced severe electric shocks, and the wires running through their machines began violently sparking and catching fire. The Carrington Event exposed a critical vulnerability. Even our most advanced traditional optical telescopes, massive curved glass mirrors positioned high above the clouds, cannot detect extreme magnetic phenomena or high-energy radiation. They are strictly bound by the limits of the visible spectrum and the distortion of Earth's atmosphere. To protect modern power grids and communication satellites from forces that can dismantle them in an instant, researchers realized that building bigger glass mirrors wouldn't work. We had to completely reinvent how we observe the universe. The first major observational barrier sits at the center of our solar system. The intense glare and extreme radiation of our own sun make it incredibly difficult to see how dangerous solar weather actually forms. This animated diagram charts the temperature of the sun. Notice how the visible surface remains relatively stable at about 6,000 degrees Kelvin. But as we move outward into the corona, the sun's invisible atmosphere, the temperature spikes violently to over 1,000,000 degrees. Because this massive energy transfer doesn't emit signals we can easily decode from Earth, physicists like Eugene Parker proposed a radical solution. To understand the origin of the solar wind, we would have to physically fly a sensor directly into that 1,000,000-degree atmosphere. Delivering a probe into the sun's orbit requires staggering power, just to overcome Earth's momentum. Engineers utilize the Delta IV Heavy, one of the most powerful boosters available, to launch a relatively tiny payload on a trajectory toward our star. The only way the Parker Solar Probe survives its close passes is through a specialized carbon composite sunshield. It absorbs heat up to 1,500 degrees, allowing the probe's delicate instruments to operate autonomously behind it at comfortable room temperature. By treating the sun as an extreme environment to survive rather than an object to photograph, scientists finally captured direct measurements of the forces driving solar storms. The second major barrier to seeing the unseeable is a matter of scale and distance. For decades, astronomers wanted to observe supermassive black holes, objects of extreme density sitting millions of light years away. Theoretical physics, guided by Albert Einstein's general relativity, predicted that these massive gravitational wells existed, but proving they were real required capturing the event horizon, the exact boundary where gravity becomes so strong that light itself cannot escape. There is an immediate optical limitation. No single dish on Earth is large enough to resolve a silhouette of that size from that far away. To see the event horizon, scientists calculated they would need a lens the size of the entire planet. They solved this by creating the Event Horizon Telescope. This project electronically linked widely separated radio observatories across the globe, using hyper-accurate atomic clocks to synchronize dishes designed to penetrate deep space dust clouds. The data collection was a logistical nightmare. The combined observatories captured 5 petabytes of information, an amount so massive it couldn't be transmitted over the internet. Researchers had to physically fly a half-ton of hard drives from remote outposts, including the South Pole, to central processing labs. Through this unprecedented global collaboration, astronomers didn't snap a standard photograph. They used algorithms to stitch together radio data, eventually revealing the unseeable silhouette of the black hole at the center of the M87 galaxy. The third observational barrier requires looking past blinding light to find a tiny shadow. Locating an Earth-sized planet orbiting a distant star is incredibly difficult because the planet's faint reflection is completely swamped by the intense glare of its host star. Satellites monitor the host star, When a planet crosses in front of it, the star's light registers a tiny, rhythmic dip. The width of this dip reveals the planet's orbital duration, and the depth tells astronomers its exact size. Astronomers verify these findings using high-accuracy spectrometers. They measure slight color shifts in the star's light, which reveal a consistent wobble caused by the gravitational pull of the unseen orbiting planet. These indirect methods have been wildly successful. Observatories have now cataloged nearly 4,000 exoplanets, including entire clusters of Earth-sized worlds located in habitable zones, like those found in the TRAPPIST-1 system. By learning to measure the subtle absences of light and faint gravitational distortions, researchers mapped thousands of new worlds that standard glass lenses could never capture. Over the past century, we have engineered brilliant workarounds for our biological limits. We built thermal shields to touch the solar wind, networked the entire globe to map a black hole, and decoded shadows to find thousands of alien worlds. But despite having the clearest view of the cosmos in human history, there is a glaring anomaly. When we observe large spiral galaxies, their outer edges rotate at speeds that completely defy our current understanding of physics. This chart shows the specific physical mismatch. The bar on the left represents all the glowing, visible mass in the galaxy. The towering bar on the right represents the massive amount of gravity actually required to keep that spinning galaxy from flying apart. The glowing stars and dust we can see do not generate nearly enough gravitational pull to hold the structure together. To explain this, astrophysicists introduced dark matter, a theoretical mass that exerts a powerful gravitational influence but interacts with absolutely no form of light or electromagnetic radiation. The scale of this unseen force is staggering. Current estimates calculate there is 5 times more dark matter in the universe than the normal matter that makes up everything we can actually see. We pushed human engineering to its absolute limits, finding ingenious ways to observe the most elusive phenomena in space. Yet the ultimate reward for seeing the unseeable was the humbling realization that 80% of our universe remains completely invisible to us.